Now let's talk about addition reactions. You can think of addition as being the opposite of elimination. Here's an example of an E2 mechanism. I have 2-bromobutane, or butane rather, 2-bromobutane. And I take a strong base like sodium methoxide. So here's the methoxide ion. A strong base because it has a negative charge. So what does a base do? It steals a proton. It's going to abstract this proton from the beta carbon, and the pair of electrons that bond that hydrogen to the carbon will become a pi bond, followed by loss of a leaving group, and we end up with an alkene. Okay, so think about that. This is bromoalkane minus HBr equals alkene. And I said addition reactions are the opposite of that. That would be alkene plus HBr yields or equals the bromoalkane. So this is an example of an addition reaction. And mechanistically, it might look like this. Here's the product we made in the elimination reaction before, and here's an HBr molecule. Okay. And what's really interesting about this is that the electrons of the pi bond can act as either a nucleophile or a base. In this case, they're going to act as a base and abstract the proton from the HBr, which will give us a carbocation intermediate. Right, so the carbon on the left got the proton and the carbon on the right became a carbocation in the way I drew this. And we also get a bromide ion. Now, the bromide ion is a very strong nucleophile. It'll perform nucleophilic attack on the carbocation. And we end up with 2-bromobutane. Bear in mind, though, this is just one possible mechanism. And there are questions that you should have at this point. How can we control this reaction? Does it always go in 2 steps? Do we always have to add a halo acid? What are the stereochemical and regiochemical considerations? Right? What are the reagents we need to use? Will the mechanism always be in 2 steps? For now, let's look at our possible outcomes. So here's a table from chapter 9 in your textbook. It's table 9.1, and it shows some common types of addition reactions. In the first, we've got a halo acid, HX, where X is chlorine, bromine, or iodine. So you can use this with HCl or HBr or HI, and you add it across a double bond, and one of the formerly sp2 hybridized carbons gets the hydrogen, and on the other side, you get the halogen, right? So we've gone from an alkene to a haloalkane. Right? We can also add water. On one side of the pi bond, we'll get a hydrogen. On the other side, we'll get an OH group. That's called hydration, right? And we go from alkene to alcohol. we can add hydrogen to both sides. In effect, get rid of the double bond. Just go from an alkene to an alkane. That's called hydrogenation. Okay. Instead of using an acid, we can use a molecule of either Cl2 or Br2 to add a halogen to both of the formerly sp2 hybridized carbon. And now we've gone from an alkene to an alkyl dihalide. Halide. Okay? If we add a hydroxyl group to one side and a halogen to the other, we make a halohydrin. And if we add a hydroxyl group to both sides, that's dihydroxylation. That gives us a diol. In all of the addition reactions that you see, one of the steps will be the pi bond acting as either a nucleophile or a base. When it's acting as a base, it's abstracting a proton. When it's acting as a nucleophile, it's performing nucleophilic attack at some electrophilic center. So, just to get you thinking about the pi bond acting as either a nucleophile or a base, think about why pi bonds are more reactive than sigma bonds. Is it A, because pi bonds have their electron density in a more accessible location outside the bond axis? Is it B, because sigma bonds have their electron density in a less accessible location along the bond axis? Is it C, that both A and B are correct? Or is option D correct, that this is a trick question and that everyone and their dog knows sigma bonds are more reactive? Pause the video now and select an answer. The answer is C. The fact that the electron density in a pi bond is located outside the bond axis makes it less stable, better able to act as either a nucleophile or a base. And whether it's acting as a nucleophile or a base depends on what reagent you choose. So addition and elimination are the reverse reaction of each other. And since they're the reverse reaction of each other, we can think of the two processes, both addition and elimination, as happening at equal rates and putting those processes at equilibrium with each other. So here on the left-hand side, we've got the alkene and the haloacid. On the right side, we've got the haloalkane, right? And addition and elimination happening in equilibrium with each other. We want to think about what are some ways we could shift the equilibrium to one direction or the other, depending on whether we want to get the alkene or the haloalkane, that is the addition product or the elimination product, and that depends on the delta G of the reaction. To evaluate delta G, we need to evaluate two things. Remember, delta G equals delta H minus T delta S, and delta G negative is favored. Okay, so delta H is enthalpy, that is bond strength, and the delta S term is entropy, which is really just the number of freely moving particles. Now we're going to look at it for a specific situation. Here I've got ethene and hydrochloric acid to make chloroethane. Okay. So for the delta H piece, the bonds are stronger in the products, right? That means delta H is negative. And this is really because the pi bond is weaker than the C to Cl sigma bond that is formed. You can see the pi bond is at 63 kilocalories per mole and the C to Cl sigma bond is 84. Okay. And we also end up with a C to H bond that is about equal to the H to Cl bond. Okay. As far as delta S goes, we are decreasing the number of freely moving particles, right? We go from 2 particles to 1 particle. That means that delta S is negative. So we've got a delta H that's negative. That favors the addition product. And a delta S that's negative, that favors the elimination product. So the fact that the two parts of delta G favor different things, delta H favoring the addition product and delta S favoring the elimination product, gives us synthetic control. Think about the equation for delta G. Delta G equals delta H minus T delta S. At low temperatures, delta H wins. At high temperatures, delta S wins. Now we can easily manipulate temperature in a laboratory setting. Use an ice bath for low temperatures. Use a hot water bath for high temperatures. So, if you use an ice bath, you're going to get the addition products. If you use a hot water bath, you'll get the elimination products.